Today we're going to look at this little worksheet called Application of Gravity's Force. The force due to gravity we've studied before, we called it weight. But where does weight come from? What's ironic is we actually don't know how gravity works. We can only describe it. And actually, Sir Isaac Newton described it really well in his law of universal gravitation, which states that the force of gravity on an object depends on this universal constant g, which he didn't measure, but a contemporary of his named Henry Cavendish measured there. And then we have the mass of each object, m1, m2, or big M, little m, depending on how you look at it, over the distance between the objects, squared. m1, m2 over the radius squared is the way to look at it there. In terms of understanding how satellites orbit, it's very important we know how strong gravity is at different distances there. And then eventually came up with this brilliant experiment, which was basically the idea of putting up heavy metal objects like lead balls and then little tiny masses there, and you could measure the force pulling on them as they gravitationally attracted with a very precise twist of a torsional device there. And since then, there's been more modern versions to try to measure gravity. What we're going to do is we're going to look at how your gravity changes depending on which planet you're on. So the first thing to do is to put in your mass in kilograms. And most people don't know their mass in kilograms. So the rule of thumb is your weight in pounds is equal to your mass divided by 2.2 is the rough conversion. So when you buy bananas in any country except America, you don't buy it in pounds, you buy it in what? In kilograms, right? So anyway, take your weight in pounds. So I think I'm around 150 now. I don't know what I am. I'll just make up something. 145, and then divide by 2.2 roughly. And I promise when I check your labs and calculations, ladies, I only look at your weight in newtons and your mass in kilograms, because it's none of my business. There you go. So anyways, I'm about 65.9 kilograms. Don't worry about units because they're already given. So the next thing we got to calculate is what is g on that planet. And here's how you get g. If you notice, if we just take this part of the equation right here, force due to gravity we call weight, g times m over the radius squared. So g is the universal gravitational constant, which was given on the previous page. You don't have to memorize it. We're just going to use this number, 6.67 times 10 to the negative 11th. So let's go ahead and put that into our calculators. This is what Cavendish measured with his torsional balance. It's a very brilliant experiment tonight there. And this is what's the universal gravitational constant for a universe. So every universe you live in has its own gravitational constant. And this is what it turns out to be for not only Earth, but our whole universe that he measured. Then we're going to multiply that by the mass of the planet. So the Earth, its mass is 6 times 10 to the 24th kilograms. So let's go ahead and take our universal gravitational constant. We're going to multiply by the mass of the Earth, 6 times 10 to the 24th. And then we divide it by the radius of the Earth right over here, right? So if we take the radius of the Earth, which is 6.4 times 10 to the 6, which is 6.4 million. And if all goes well, boom, we get 9.77. Though on the surface of the Earth, it's usually closer to 9.81, actually, depending on if you're at sea level. So here's what's kind of weird. If you look at this equation, technically, as you go higher above the Earth, what happens to gravity? You're further from the center, right? So as you get further from the center of the Earth, as you go further out, what do you think? Gravity gets stronger or weaker? You're further from that center of that black hole? It's actually weaker. So when you actually figure out satellites and things like that, it actually makes a difference how high up you are. So how would you find your weight in newtons? You just take your mass and you multiply it by what? By the value of g that we get, right? So let's go ahead and do that on our calculators. Times, actually, you know what? Let's round that to 9.8 because that's what we're used to. I don't want to throw you guys off. And for the other planets, we'll do 2 decimal places. 65.9 times 9.8. And we're getting 645, in my case, 0.8 newtons. If you divide your newtons by 4.45, that will give you your roughly 145.12. And ladies, I promise I won't look at that last column. None of my business.